Okay, Year 12, here is the final piece of the jigsaw. We have covered everything in Chapter 4 and 5, how circuits go together, what's the basis of calculating anything about them, and Section 5 or Chapter 5, all of the things that cause those effects to happen. So the idea of delivering energy around the circuit, the power, the rate at which it's delivered, all stems on the behaviour of the materials within it. And this is no different if we're talking about the source of the energy, so where the EMF comes from. Okay, so our final chunk today is actually going to be looking at the source of EMF, energy into the circuit, energy given to the electrons to make them work. So as our little blue electrons come out and return, and for those that have done chemistry, half equations, you're already a little bit a step here. But yeah, as our electrons come in and out, it all depends on the reactivity of the electrodes within this compound here. So this compound we call an electrolyte. It has polarity within it. It has an ability for it to have its energy removed by removing the charges, breaking down, etc. So as we break down the molecules in contact with each electrode, some of them will release more energy than others. So for example here, our green electrodes are the same material, different from the red electrodes. And the polarity, the reactivity of the green is more than the red, and so the voltage ends up higher here. So the negative potential is higher here than it is on the red one. And so electrons effectively are excessive over here, we get electrons coming out. So that's the basis behind this. However, what we're going to talk about, this idea of efficiently getting EMF from a cell, is very similar to efficiently getting EMF from other sources, so mainly generators. The processes we're going to keep generic, but actually the ideas are exactly the same. So within here, what's going on? Well, we release the electrons, we give them energy. That was our definition for EMF. However, none of it is perfect. Okay, none of this is energy free or energy loss free. So within the bonding itself, within the process of getting them out, it all requires energy to make it happen. So there will be some energy loss that comes out, slightly warming the material, for example, where the reactions happen, and that energy loss means that we're not getting 100% of the potential, the theoretical energy from it. Again, there's a lot of research still going into batteries to make them more and more efficient, to try and make them work better, and so that we can reuse them, which is another challenge. So let's have a look at the chapter and see what we do with it, so we can cheat ever so slightly at this point. Now the experiment should make this clear, but what we're going to do is work on the idea of EMF giving energy to, as I say, two charges, and the PD's taking it from it. However, this idea of what's going on is slightly more complex. We're going to treat it in a similar way to what we've done already. So to start with, let's just go back to our basics. What do we mean by EMF? And this is the energy released or energy gained. Okay, might be a way of thinking about it, but I'm going to go with released by the chemical reaction. Or magnetic field. Okay, so in a generator we're starting to talk about the energy surrounding magnets and the interaction with their electricity, so electromagnetism comes out of this. There are other ways of generating a voltage, as they say, producing an EMF, but these are the main two by a long way, so we'll just concentrate on these. So energy be released by that, or by magnetic field per unit charge. Okay, so per unit of charge. In other words, epsilon is the work done given to each charge. Okay, so again, nothing new, just tightening it up ever so slightly because we're starting to think about where it's coming from. Now, when you buy a battery, of course, it tells you what the EMF is. Okay, except it's only true when it's in the packet. As soon as current starts to flow, it won't be that value that it's stated on the battery, okay, or on the cell, or on the generator, the theoretical value. Why? Because you lose energy. So again, maybe this is an exam type question. EMF is only what you get across the terminals, i.e. where you connect your wires, when no current flows. Okay. So if you go back to Kirchhoff's second law, and we'll put an equal sign there, don't know why that's not come out as equal sign. If you go back to Kirchhoff's second law, it's about conservation of energy. And yet I'm saying that energy is lost, so this can't be true. Well, we can get around this fact if we think of having a tiny resistance, because the energy loss is quite small, a tiny resistance within the cell. Okay, so if we just go back to our diagram there, what we can do is we think of our electrodes, our positive and our negative end, and we're just going to treat it as though instead of drawing our cell like that, I know I've actually got two cells here, so that's a battery, but if we draw a cell like that, we'll just pretend it has a little internal resistance, which we use a little r for. Okay, so when we connect that, you might have noticed it in questions already, we pretend that inside the packet that you buy, the cylinder that says 1.5 volts on top of it, well, we do have the 1.5 volts, but we also lose a bit of energy inside. When we don't have any current, we don't have any energy loss. So when that's zero, that's zero. Okay, excuse me, correct that. For my little resistor, when that's zero, that's zero. So as soon as current flows, you are taking off a bit of voltage, and as you should find from your experiment, the bigger the current is, the bigger the voltage dropped inside the cell, the energy loss inside the cell. So what we have is we're going to think about the battery as a whole, that includes both of them, and we're going to look at what comes out of the terminals. So we will call this the terminal voltage. So if you stick a voltmeter on your power supply, it's actually what you get out, it's not necessarily what's being created. Okay, so little r, very simple. Okay, we put that in, we think about what's going on inside, and it's really nice and straightforward. So if we just treat, I can get that past the computer, there we go. If we treat that internal resistance, if we treat that energy loss as energy loss from some tiny resistance, you'll find that your circuit becomes ever so slightly more complicated. You just have another resistor in it. Okay, series and parallel doesn't really matter, but the voltage going to the circuit is not quite what you've got there. Now in terms of the mathematics, it just means that we have to add on another IR onto all our calculations. Difficult? Not really. So let's go for the basics. In our circuit here, what we've got is the sum of the EMFs, okay, equals the sum, so excuse me, terrible sigma, sum of the PDs, which is IR. Okay, so that's our PD there. Now what we can do in this case is we can think of that in terms of Kirchhoff's second laws as just the voltages, which make it a bit easier. So sum of EMF equals voltage across my little resistor plus voltage across my big resistor. Okay, so that PD plus that PD equals what we started with. Okay, and if we break that down a little bit, we end up with I little r plus I large r, where R is the load, the circuit that you connect to it. I little r is the energy lost inside. So this is your lost PD, and this is your, the phrase goes, terminal PD. Now if there is more than one resistance outside, again it's what comes out of the battery, so it's still the total voltage being given to the circuit. So I'm going to put that, to make that clearer, circuit resistance. Doesn't fit in the box, but we'll go with that. Okay, now in your data book, it's actually written, it's got its own separate equation, which is just simply that neatened up, R plus big R. But if you think about it, it's just adding up the voltages. So that equation, just be a little wary. You can't use it for everything, but you could use it for any circuit with two resistances in, so you can use it in a way. But yeah, basically it's just adding up the PDs, including the one that's lost, to give you your output from your cell. Okay, so this is your, as I say, cell output. Might be a way of thinking about it. I tend to call that V out, okay, because it comes out. Now in terms of perhaps a better way of thinking about this, I know this is an easy way of doing it, it's just resistances, but in terms of what you've got, I would say your V out, so I'm going to change my language ever so slightly from that, that's going to be your epsilon, your EMF, subtract I little r. And I think that's a useful equation. Okay, so as soon as you get current, you're getting a little bit subtracted off. If, of course, there's no current, there's nothing subtracted off. Okay, so that's quite a nice, powerful little thing, but that's what actually goes to the circuit after you've subtracted a bit. Okay, so that's kind of good, but it does mean that you're losing energy. Your circuit now, no matter how good your actual device that you're connecting to your battery or your power supply, it's not perfect. You're already on a hiding to nothing. You've lost energy, okay, which has to fit in with the laws of thermodynamics, the laws of energy. Now what we can do in the experiment is we can find out what these values are, because you can't measure them directly. You can't, unless of course it says on the cell, you don't know what they are. So if we just take that idea that I've left up here, then we can start thinking about how to do it. So this again is one of our really big experiments. Why? Because it applies to so many things. So what we would do is we would measure the EMF and internal resistance. We can't do that, but we can measure voltage and current. Okay, so measuring current, measuring the PD in a resistive circuit, and plotting the results. Well, obviously if you just had one resistor, you'd end up with one current, one PD, and that would be a graph with one plot on. So what we'll do is change the actual loads that are connected, change the resistance connected to the battery. So crucially, like with all questions and the practicals, but all questions about planning practicals, for a range, ideally a wide range, but a range of and I'm going to call it load resistances, okay, i.e. circuit resistances. So if you do that, what you'll find is that you'll end up changing this. So you'll end up changing that. That won't change. That's one of your constants. That's one of your constants. Now, if you look at that and rearrange it ever so slightly, you'll get a fairly obvious pattern from your graph. Okay, so we already know what the results should look like in their shape. The values will depend, of course, on the graph. So if I just take that, we've got, as I say, V out is going to depend on the rest. Okay, so I'm going to have epsilon minus IR as we had. I'm going to swap that around a little bit because that is going to depend on my variable there. Okay, so I'm going to change my resistance to get these different things. So for a range of resistances, what I can do is find, for this, then I can find the voltage out and I can find what happens to this. So I'm going to just swap that to be V out equals minus IR plus epsilon. So I'm going to just swap those around. Why? Well, that's my dependent variable. So I'm going to plot that on my y-axis. That current is going to be what I'm changing with my load. I'm not interested in load resistance. That's what I'm going to change, but what I'm actually interested in is current. So if I plot that on my x-axis, we know that that will give us a gradient M. It will be negative because I've got a negative sign there, and I'm going to have an intercept C. So what I've got is I can simply read those off a nice straight line graph. So if I plot that, I should get, with I flowing through my circuit on the x-axis, if I plot the output voltage, the terminal voltage on that one, I should get a graph that does that. That is my value of EMF, i.e. the maximum voltage when current is 0. Okay, so when current is 0, that's our definition, isn't it? And gradient will be minus R. Okay, minus and the R. So I can easily find the internal resistance of my setup. I can easily find the maximum EMF. That's quite simple anyway. I could just turn off the current, make it open circuit. Bit difficult because of course voltmeters do have resistance, so that won't be perfect, but we can do it from a change of results and extrapolate our graph backwards. So if we get readings that give a good range, we can follow that back until it hits the 0 current value. Now we want to deliver power, and the power that we get into a circuit, and it doesn't just matter with batteries here, but a whole kind of other things as well. I should say this will work with AC. This will also work with other alternating systems, so we can use exactly the same thinking with, for example, waves, if we're trying to deliver waves to somewhere. For radio set, for example, a transmission system, or even in things like ultrasound scanning, it works in a very, very similar way. Okay, this idea of how much we lose as it gets as things happen. So, as it says here, if we want to get the most out of the load, then what we need to do is think about trying to minimize the loss here, the loss due to the internal resistance. It'll never be 0 as soon as current flows. It's always going to be there, but we can get around it. So if we take this equation and use it to calculate power, power out, power being created and power being lost, then we can compare and get the best readings. Okay, so I'm going to go back to my original equation, the data book equation, and then multiply it out. So I'll do it in one go. So from our notes, we've got epsilon equals I little r plus I big R. It does not matter which way round you put those two. Okay, so if I multiply through by the right value, I can get power. Okay, epsilon is a voltage. How do I get power with voltage on its own? Well, I could square it and divide by R, but that's a bit complicated. So what about the other option, which is of course P equals IV? So as we get that, if I take that voltage, different type of voltage this time, I can still multiply by I. So epsilon I equals I squared. So I'm multiplying both sides by my current, so I squared, that gives me power as well, plus again I squared big R. So power loss inside, power delivered, power being created or released in the chemical reaction in the first place, that's what's going to give us our full values of what's happening. Now, as that gets bigger, these get smaller, therefore this gets smaller, so that's one way of doing it, but of course that means that this gets smaller as well. So it's not just simply a case of trying to minimize that, it's actually that balance between the two. Now if we play around with impedance matching, and again we will meet this right at the end of next year when we're talking about impedance being the wave travelling into an ultrasound scanner, okay, from for example examining a fetus in the womb. We have a similar idea with impedance matching. So we want to maximize the energy going from here to here by minimizing that. And ideally, I want to get you trying this with your results, mainly because you're going to experiment a little bit with Excel, putting the equations into Excel with your currents and voltages that you've measured. But what you should find is that you will get this actually working up our power delivered, okay? Maximum power to circuit is always going to be only 50%. Okay, so we will always lose energy inside, but when our two resistances are equal, and I'm just going to change that to our little r, so where I've got my little internal resistance, when it equals the load resistance, then that is when you'll get your peak there. So this is the power actually delivered to the circuit. So this is the power I'll say delivered to R, okay, to our load. In terms of the amount lost, again you can kind of do the reverse of that. It will be a minimum, it won't be zero, but it will be a minimum there. So power loss or lost in little r. Okay, so again, minimum, going to get maximum there. When does it happen? When the resistance outside and the resistance inside are equal. And you'll find that with waves as well. Okay, how do you get the most out of your stereo in your car? When you wire it up to your speaker, you've got to have the same resistance of speaker and circuit. Otherwise, you don't deliver maximum power. Okay, so linking that back, maybe a little bit about this, but more to do with this, back to our common sense approach that we had a couple of lessons ago. How to get the best power out of a circuit? Well, it depends what you want from your circuit, but we can connect cells together in series or parallel to make that work. Okay, and just like with any other series circuit, you can figure out what's going on. It's kind of common sense, but you just got to remember you've got a little bit of energy loss at each one, no matter how you connect them. Okay, so linking this in, I'll just get rid of this a second to clarify. There we go. But it does link into what's happening inside if they're chemical cells. So what we've got going on here is I've got, for example, 1.5 volts, 1.5 plus another 1.5 plus another 1.5. So my total EMF is going to equal 4.5 volts. Okay. but I'm going to lose a bit of energy there, and a bit of energy there, and a bit of energy there. So my total resistance inside is going to be 3R. Okay, it's bigger. So although we're making a bigger voltage, we're giving more energy to the charges, we're also losing more energy from the charges. Okay, so doing this actually will still limit the delivery of energy. Even though we're turning the voltage up, we're giving all the charges more energy. The charges still have to go through every single resistor. Okay, so even if we drew them at the end, they still have to go through all 3 resistors. Now, if we put them in parallel, we're only going to get a drop from here to here from each of them. So whichever way the charges go, whichever battery they go through, whichever cell they go through, they're still only going to gain a third of the energy. However, you've got a choice. So again, you've got resistors in parallel. So resistance is basically R divided by 3. So it's actually 9 times easier for the current to flow through them in parallel than it is through in series. And in terms of this, if you think about what that means, reactions happening at each surface, let's just consider the red ones for example, well, the reaction here is then kind of semi-neutralized by that, which is then reboosted by that, so actually you're losing quite a lot of energy as we've displayed there. But actually if you had separate batteries, well, you can get 3 times the charge flowing through, and so you can actually deliver energy faster to those charges. So you have a more powerful output using that. And in terms of going back to, our diagram, our graph that we've just had, effectively we're reducing the resistance here, so you can make it work on lower resistance circuits. In other words, circuits that need a lot of power. So, just like putting bulbs in parallel, putting cells in parallel is also the best way to deliver energy at a faster rate. Okay, so parallel circuits is going to give you greater power delivery, power given out by the batteries, bulbs, whatever you've got in your circuit, everything connected. Okay, so if this was solar cells, we've got the same difference. It's not a chemical effect, it will be a photovoltaic effect, photoelectric effect, producing that voltage, releasing those charges. But again, we have that effectively work function taking some of our energy away. Okay, so we can connect them in parallel. They'll give us more current, which means we can actually make more things run. We can deliver that energy faster. But if you need a big enough voltage, well, then maybe we have a bit of series and a bit of parallel. So maybe in series we'll have packs of 3 or 5 in parallel. Okay, so you can have clumps, clump, and that will build up your voltage, but in the end you've got to have the parallel bit to make it work more powerfully. Okay, so have a go with the final questions. Okay, they're very straightforward because they're literally, it's just adding up the PDs in a circuit, but the idea is really, really useful. I say lots of applications, and it does mean that they tend to ask lots and lots of questions. So again, there's a few questions in the back to kind of have a work through. You can expect them in questions. So here we have blah 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 blah, and you've got a bit of an internal resistance, so just draw it in as an extra resistor. Quite common is, you will have spotted already, I'm sure, where they will start with a circuit and say it has negligible internal resistance. In other words, ignore the internal resistance because it's so small. And then what happens if you have a larger internal resistance? What happens as that gets larger? Well, don't worry too much about the power, just more simply, you've now got more resistance, so you lose some voltage. Okay, so again, think of it as voltage loss. Okay, and that's really powerful. So again, voltage going to the circuit, the more that is, the more you lose. Okay, so the more energy you lose in the process. So really, really common question, often the last bit as a description. What happens when you have internal resistance? Just means there's less current delivered, therefore less power delivered, therefore you've lost energy on the way. Okay guys, thanks for that, and revise hard, because electric circuits is one of those things where people do find things a little bit difficult, but they're not. Just keep going back. It's Kirchhoff's laws, it's V equals IR to give you PD, and the idea that nothing is perfect to give you that power delivery. So the equations for I squared R, etc., keep using them. It's all about those 4 sections. So now we have finished the last chapter. Go to the last page before the cartoons, and there's a really nice little summary there, just to kind of link everything together. Okay, so a simple circuit, write stuff on. You've got your EMF, you've got your lost voltage, you've got things like going on like that. You have stuff about your key properties of resistance, what affects it, the length, the area, and so on. What's going on here, etc., etc. Okay, so really nice kind of final ending to the chapter to just get your head sorted, so you've got a clear idea. The maths is easy on this bit, much less confusing than it is on the circuits, but can you describe it? Okay, thank you very much, Year 12. Cheers.